recording. All right, so guys, as you look over your books, chapter 6, right? So what I'd like you to do is not start at the beginning of chapter 6. We're going to look at this together sort of in its entirety. But guys, and I know it's been a while since you did that chapter summary. This might be a little bit distant in your memories. But guys, if you turn back to maybe a good, so turn back to page 220. So guys, as you go back to page 220, I think you probably had the experience, I hope you had the experience, that when you got back to page 220, you were like, oh, this sounds familiar. I got my S's, I got my P's, I got my D's, I got my F's. I've got those like blurry pictures of electrons being clouds, like the fan blades, like the rubber bands, like this. And then you look down on the corner of page 221, and you've sort of got that rung ladder type diagram where you've got the 1s and the 2s and the 2p and the 3s and the 3p. And maybe you were remembering back to that day that that's actually the structure around which the periodic table was developed. We didn't talk about this last year, but I think you guys are insightful enough. You understand this. Guys, the periodic table was put together in the mid-1800s by a guy named Mendeleev. And guys, they didn't even know about electrons. Thomson had barely been born. They didn't know about electrons, and Mendeleev put the periodic table together, came up with this, and then when we discovered electrons, it perfectly followed the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p thing. You understand, though, that wasn't a coincidence. How did Mendeleev put the periodic table together so that it perfectly mapped onto their electron structures? Do you know? What did Mendeleev do?
With valence electrons.
We didn't know about electrons. How did Mendeleev put the periodic table together? Based on what? Reactivity, based upon properties. So he put all of the elements in group number 1 together because they all reacted the same. And group 2, they all reacted the same. And skipping over the transition elements, group 3, 4, on through 8, they all reacted the same. So he grouped them together by reactivity, and then he put them in order by increasing weight. And he's actually the one that proposed that it doubles back on itself. And he put this thing in order by reactivity. So guys, what's the connection? How then did that line up perfectly with S, P, D, and F? What determines their reactivity? Exactly. So it's not a coincidence that they perfectly line up, because their valence electron structures are the things that determine how they react. And so we would expect then the two to line up, and in fact they did. So as we continue on, we got our 1s, 2s, 2p stuff. Then guys, 223. At the bottom, we now start talking about orbitals, and at the bottom of 223, we've got the S's, and then on the next page, 225, we've got the P's, and then on 226, we've got the D's. On 227, we've got spin, and they talk about parallel and anti-parallel spins on 228. Then we start doing orbital filling diagrams on 229 and 230. Then on 233, it relates to the periodic table, and it continues through the periodic table. 237, it starts to talk about why some of these atoms don't follow the trends on the periodic table, and then it stops. And that's the end of the unit, the end of the chapter. So guys, going back then again, maybe with me, you'll notice that this entire conversation started on 220 and ended on 238. So basically this space right here was electron structures from general chemistry, and we're not going to redo this year. This is what we're going to do. But it's only the last half of the chapter. So what's the first half of the chapter about? Well, go to the first page of the chapter. Guys, when you go back to page 206, Sorry. When you go back to page 206, you'll notice on 207 it says electron structures of atoms, because they don't show you a picture of an atom on 206. What do they show you? Sorry, he's persistent. Oh, hold on. My watch is locked and it didn't hang up on him. Sorry, let me just mute that. So guys, what does it show you on page 206? Lights. Weird, right? So guys, what they're trying to do here on these first two pages is subliminally set up kind of a dichotomy. Because on the right-hand side, you see electron structures, and on the left-hand side, you see lights. They didn't show you electrons, they showed you lights. And then guys, what is the first half of this chapter about? Light. Why? Why would a chapter about electrons start with light? But why do we care about electromagnetic waves if we're studying electrons? Go ahead. Okay, so guys, maybe we should try this. You understand fundamentally the reason you're taking advanced science classes in high school is not to prepare you for a career in science or medicine. The reason that you're taking these advanced classes is so that you can answer your children's questions when a 5-year-old comes and tugs on your shoulder and says, "Hey, Daddy, why is the sky blue?" And, "Hey, Mommy, why is the sunset red?" And where does light come from? And why does it rain? Guys, rain is not God crying. You better have an answer, right? So let's not raise another generation of stupid people. Because, guys, we need answers to kids' questions. So when Junior comes to you and, Mommy, where does light come from? The answer is not light bulbs. Guys, what's the answer? Where does light come from? Falling electrons. And then you get to have a neat conversation with your 5-year-old about atoms and the fact that you and everything around you is made of these little tiny things. And feel free to tell them it looks like a solar system, and hopefully you've already explained that to them. And then they understand that there's these little bitty particles going around in circles, and when they fall, they release energy. Just like when you drop a book releases energy in the form of sound, well, falling electrons release energy in the form of light. Please don't, though, explain to your children that when an electron falls, it falls down and hits the nucleus and makes a clapping sound and light comes out. That's where this and the book are a little bit different. But guys, understand that that's why we're studying light. Because Mommy, where does light come from? And the answer is falling electrons, right? You okay with that? Well, so do all falling electrons release light? And the answer is no. All falling electrons release electromagnetic radiation, of which light is a very specific band. Some falling electrons release infrared. Some falling electrons release ultraviolet. Some falling electrons release X-rays. It depends on the thing that's falling and how far it's falling. But all falling particles release, just a second, all falling particles release electromagnetic radiation. Now here's the disturbing thing. When you walk, when you move, you're also releasing electromagnetic radiation. Anything with mass that moves releases electromagnetic radiation. The problem is we're so big and we're moving so slow that it's undetectable, but it's there. We don't look at the equation anymore that allows you to calculate it, but you can actually calculate the frequency of light, the wavelength of light that you release as you're walking out to your car this afternoon. Yeah, so anything that's moving releases electromagnetic radiation. Yeah, we'll leave it at that for now. Go ahead.
So you said that there's light, it's a small spectrum, and then the rest is like radiation.
Mm-hmm.
All that stuff.
It's all radiation. Light is radiation.
So I thought it was all considered light.
No.
Yeah.
It's no. So guys, this provides a wonderful segue. So let's make the transition right now. Obviously, you don't need to write any of this down, but the connection within our chapter 6, guys, the connection is this: that at the turn of the 1900s, when Rutherford did his work with the gold foil, he proposed the nucleus. But he had nothing to say about electrons. he was still adhering to Thomson's plum pudding model that said that the electrons were simply randomly distributed throughout space within these atoms. Well, it turns out, and I don't know if you guys knew this, one of Rutherford's graduate students was Niels Bohr. Did you know that? That actually the gold foil experiment, Niels Bohr was actually a part of that. He was one of Rutherford's graduate students. Anyway, so Niels Bohr came along and said, okay, we've figured out some things about the nucleus. Now let's start thinking about electrons. And so as we know, he added energy to electrons, and we should talk about the terms. When an electron's in its lowest energy place, what do we call that? Ground state. Add energy, it jumps up to an excited state, and then when it falls, it re-radiates that energy in the form of light. Well, guys, because we're talking, and so the energy that they radiate is a function of their mass and the distance that they fell. Now understand, because we're always talking about electrons, their mass is constant. So if their mass is the same, because it's always electrons, then what is it that determines the energy of the light that's emitted? How far they fell. And do you remember what we talked about last year? Short falls release what kind of light? Red light, which is low energy light, which you're going to find out in a minute is long wavelength light. And then longer falls release higher energy light, which is shorter wavelength light. But guys, all of this is a portion of what is called the electromagnetic spectrum. And guys, this is probably where you want to pick up. So guys, why do we talk about light when we're studying electrons? Well, the answer is because much of our understanding of electron structure comes from the study of the emission and absorption of light as these electrons are excited and then allowed to release the energy that they've absorbed. So guys, light is a type of what is called electromagnetic radiation. So we can talk about, well, you're catching up, never mind. We okay? So guys, what is electromagnetic radiation? And we're not going to try to get into this significantly, but it's got two components. It's got an electrical component and it's got a magnetic component. That's where electromagnetic radiation comes from. What you need to know about electromagnetic radiation is that electromagnetic radiation is a form of energy that has a wave-like characteristic and it can travel through a vacuum. So unlike sound, which needs a medium through which it can travel, guys, electromagnetic radiation, light, it travels through a vacuum. It does not need a medium through which it can transfer. How you doing so far? You okay? Okay, so ready for this one? How fast does it travel through a vacuum? Surprisingly, the speed of light. But guys, understand all electromagnetic radiation travels at the speed of light. So what is the speed of light? Well guys, the speed of light is 2.998 times 10 to the 8th meters per second. So this would be a good time to grab your AP equation sheets. And guys, let's take a look. Yeah, so I think even the book uses 3, doesn't it? Okay, so guys, you're comfortable with this, I hope. There will always be discrepancies between our book and the AP equation sheet. Another example of that is our delta H, delta S, and delta G equations. And remember that the AP equation sheet doesn't include the N for number of moles, but we know it needs to be there. So we're comfortable with the idea that there's discrepancies. So again, the number that the book uses for the speed of light is not the same as the AP test. But in either case, it doesn't matter because you don't have to memorize it because it's on the equation sheet. So the book uses 3, the AP test uses 2.998 times 10 to the negative 8th. So what you'll see is that I'll typically use this number because it's the one that's on the AP equation sheet. No, this one. Yeah, yeah. You guys good? You get the idea? Okay. So again then, guys, the question is, what travels at the speed of light? Well, the answer, of course, is light, but that's not the only thing that travels at the speed of light. Guys, all of this stuff travels at the speed of light. Guys, this is what is called the electromagnetic spectrum. So let me give you a second, forgive the pun, because it's definitely not appropriate today, but we'll try it. Let me give you a second to absorb. I know. Sorry. I'm seriously bordering on delirium. Guys, let me give you a second to just sort of take in all the information that is here. This is significant. And we're actually going to look at this twice. There's another form of this that I'd like to show you. But I like this one because it's very pictorial. Right. So guys, let's start down here at the left and let's talk about what we're talking about. So what does all of this have in common? Well, all of these are forms of electromagnetic radiation. And the problem is that when you see this, it looks like it's chunked up so clearly that radio waves are distinctly different from microwaves, from infrared, from visible light, and so on. And guys, that is not the case. All of these things, from radio waves all the way up to gamma rays, remember last year when you learned about alpha, beta, and gamma decay? Guys, all of these different types, if you will, of electromagnetic radiation are exactly the same thing. The only difference is the wavelength. It's like the difference between a low note and a high note when you're thinking about sounds. We understand that sound is sound. Some of it's long wavelength, some of it's short wavelength. But guys, we get that sound is sound. It's not like low notes and high notes are made of different things. Well, guys, the same thing is true here. Radio waves and gamma rays are the same things, just with different wavelengths. So let's talk about scale here. So guys, you go out in your car and you tune into KOHS. Well guys, the waves that are coming off of the KOHS tower have a wavelength. And guys, we'll talk more about this later, but fundamentally you understand waves repeat themselves, right? And you'll find out in a minute that the wavelength is the distance between two repeated places. So that could be crest to crest, trough to trough, point of inflection to point of inflection, doesn't matter. The wavelength is the distance between two repeated points. So guys, a radio wave is on the order of 1 meter to 1,000 meters long. Can you kind of put that into perspective? So it's 1 meter to about 1,000 meters long. So when you tune into a radio station, the waves that are making your antenna jiggle that then get converted into sound inside your car, because those waves are about 1 to 100 to 1,000 meters long. Yeah. No, so that's a good question, and we're going to talk about amplitude in just a minute. You're going to find out that amplitude does not play into what we're going to do with waves. Amplitude is not an important concept. Let us get to, we're going to be a slide ahead, and then we'll talk about why we don't need to talk about amplitude. Okay, so guys, do this with me though, just for a second. I'm sorry, I forget. What is the radio station for KOHS? Do any of you know? Okay, so 91.7. So guys, that is the radio station for KOHS. What are the units? So guys, the radio station is 91.7 megahertz. So guys, what that is actually telling you is the number of waves that go past a point in any given amount of time. So there's 91.7 million KOHS waves that come flying off of that tower in a second. That's what the radio stations are. So if you listen to 107.5, there's 107.5 million waves coming off the tower in a second. So guys, what you think of as simply being radio stations are actually the frequency with which these waves are coming off the tower. Now, the thing that's interesting is if you know the frequency, you can then calculate the wavelength, and we're going to do that in a minute. So if, and I trust you guys, if KOHS is 91.7 megahertz, that tells you how many waves are coming off the tower in a second. We can actually then figure out the length of the wave down to the centimeter. They're related, and we'll talk more in a minute. So radio waves are on the order of about the size of a building. So then we get shorter, and now we're down to microwaves. Guys, microwaves are somewhere on the order of about a grain of sugar. Again, microwaves, just like are in your microwave oven, those waves are around a millimeter, somewhere in that area. Going shorter, somewhere on the order of the size of a protozoa, are infrared light. We call it infrared light because we're pushing into the visible spectrum. But guys, if you think about like single cell organisms, a single cell organism is about the size of a wavelength of microwave energy. That's why, have you guys ever done this? You never have. When you open up your microwave oven, have you ever tried to look through the window? Why isn't it just a pane of glass? Well, the reason, because the microwaves can get through and they can get out and hurt you. So how do they block the microwaves? They call it it's just that metal mesh. And guys, the holes inside of that metal mesh allow you to see through because visible light can get through, but it's actually just the right size that it disrupts the microwaves based upon the wavelength of the energy. So when you go home today, look at the door on your microwave and you'll see the little holes. That's not the size of a wavelength of microwave radiation. But the thing that's cool, if you want to try this, you can actually measure it. If you, and it's a good excuse to eat chocolate, get some Hershey bars, the big ones, and not with nuts in it, but get a couple Hershey, Google this and look it up on YouTube. But if you take Hershey bars and actually set them in the bottom of a big glass baking casserole dish, and if you set them in the bottom of the microwave, and if you turn off the turntable so it doesn't move, and if you melt them slowly and carefully in the microwave, you can actually see the ridges and valleys in the surface of the chocolate that is the wavelength of the microwaves. Yeah, it's pretty cool. And again, it's a good excuse to eat chocolate. Look it up on Google it on YouTube if that's a thing, and you'll see. So now, guys, we get into the visible spectrum. So what's so special about the visible spectrum? Why do we call this light and all the rest of this stuff we don't think of as light? So guys, what is so special about visible light? And guys, the answer is because we exist. Guys, you've got to understand color is not a thing. Color only exists because people are here. This gets a little metaphysical, but guys, you've got to understand the difference between yellow light and radio waves is functionally, they're the same thing. The only reason that light gets this special consideration is because the rods and cones in our eyes have either been created or evolved so that they are specifically tuned to this narrow band of radiation that we call visible light. And guys, the only difference between red light and violet light and all the colors of the rainbow is simply the wavelength and also the frequency, because those go hand in hand, of the energy. And guys, these molecules in our eyes that we call making up rods and cones are tuned to this very narrow band of radiation. And as a result, this is important to us because one of the ways we interact with our world is by collecting this radiation and turning it into things that we can think about because we think about light. But guys, understand light is a human experience. And the only thing that makes it special is our eyes are attuned to this very narrow band that we call visible light. Do you get the idea? So why is it that our eyes are tuned to these very special wavelengths and frequencies of energy? And guys, frankly, the reason is because of the molecules that we see with. And you can look this up later. But functionally what happens when the light goes into our eye, what it actually does is it takes these molecules and twists them. And when it twists them, depending on the energy, the wavelength, the energy of the light, low energy light twists it a little bit, higher energy light twists it more, and that twisting actually creates a current. And that current then gets picked up by our optical nerves, that gets relayed to our brain, and our brain goes, this much twist is this color, and we interpret that as color and shape and form and vision. But guys, understand all of this relates back to these molecules, and when light hits them, they twist, and that's the beginning of our experience of sight. And if those molecules had a different size or a different shape, we could see other bands of the electromagnetic spectrum. It's just not the way our eyes have either been created or evolved. We just happen to be experiencing this narrow band that we call light. Crazy, right? Yeah. And guys, understand my explanation of twisting and things like, it's good, but it's not, obviously it's not complete, but look it up if you're interested. It's pretty fascinating. So guys, what happens if this light becomes higher energy and therefore shorter wavelength? Well, then we get into the ultraviolet spectrum, which is on the order of the size of molecules in terms of its wavelength. Again, higher energy, even higher energy as we get into X-rays. The wavelength of X-rays is on the order of the size of atoms. And then guys, when we get into gamma rays, we're starting to talk about energy that is on the order of the size of nuclei, which shouldn't be a surprise to you, because where do gamma rays come from? The nuclei of atoms, right? That's not a coincidence. So this is what we call the electromagnetic spectrum. You okay? Questions, thoughts, things you want to talk about? You guys good? Okay, so we talked about this idea of wavelength, right? So now let's switch slides, and guys, be really careful here. Well, here, let me zoom back in. What's on the left, long or short wavelength? Long. And on the right? Short. So as this sits, this goes Roy G. Biv, right? The colors of the rainbow. Red over here, low energy, long wavelength. Violet over there, short energy. I'm sorry, high energy, short wavelength. And guys, it's going to switch. Did you see what happened? Don't let this confuse you. It flipped over. So now in the previous slide, gamma rays were here and now they're there. And previously radio was there and now it's here. It's the same spectrum. It's just flipped. But guys, the reason that I was willing to expose you to something that's flipped around is because I think this does a really nice job of tying some ideas together. And that is the relationship between wavelength, which we've already talked about, right? This is 1,000. So radio waves are like a kilometer long, and then gamma rays are beneath 10 to the negative 11th meters long. But guys, now it brings in this idea of frequency. So let's talk about frequency, and then we're going to I'll give you some notes that you can write down. But guys, here's a great way to understand frequency. Right in there. Okay, so have you all been to the ocean? If not, you've waves, right? Waves crashing in. And guys, understand that electromagnetic waves are not like ocean waves. They don't need a medium. But what about frequency? Well, guys, imagine that you're sitting on the Pacific coast and you've got a stopwatch. And you're watching these waves crash in. And you start a watch and you let it go for a minute. And during that minute, you go 1 wave, 2 waves, 3 waves. And over a minute, you count 11 waves. You now know the frequency of the ocean. It's 11 waves per minute. And so the units for that would be waves per minute, and you now know the frequency of the ocean. Well, guys, just like ocean waves, electromagnetic waves also have a frequency. But as you might suspect, minutes are a ridiculously large amount of time when you're talking about radio waves or gamma rays. So instead, we use seconds. So guys, notice that the units for this are inverse seconds. So it's events per second. You know the negative exponent moves it to the denominator. So it's events per second. So when we're talking about, is this high or low energy? What? High energy, right? High energy. So if it's high energy, what is its wavelength? Long or short? Short. Super high frequency. 10 to the 20th. And guys, I fear I may have said this not well. Remember how I said if we knew the radio station for KOHS, we could figure out how many waves are coming off of that tower? That's not the best way to think of it. It's not like that KOHS tower is like shooting waves. It's this wave is continually being radiated by the tower, and in a second, what would that be, radio waves? So about 1 million, somewhere on the order of 1 million. So the wave that comes off of that tower turns over about 1 million times a second. Okay, so when we're down here at gamma rays, we're talking about waves that turn over on the order of 10 to the 20th times a second. Almost a mole, yeah, which kind of, it's 1,000 times smaller, right? But it helps you understand how stupid big that number is. But when we're down here, we're talking about on the order of like 10,000, which is still a lot, but when you're traveling the speed of light, it's really not that many. So guys, the thought then is low energy light tends to be long wavelength, low frequency, and then high energy is short wavelength, high frequency energy. Do you get the idea? You okay? Okay. So guys, let's pull all of this together then into something that you can chew on. So here are the things that you need to know about waves. It might not be a bad idea to scratch this down in some form. So guys, when we talk about waves, there's some terminology that we need to share in common. And Matt, this is where we're going to talk about amplitude. Did you get your drawing done? So guys, let me define for you the two things that we need to talk about, and then we'll get into this a little deeper after you've got your notes written down. So when we talk about waves, we are going to talk about the two things that we discussed on the previous slide, frequency and wavelength. We're not going to talk about amplitude, and we'll explain why in a minute. So let's define the things we are going to talk about, and then we'll talk about why we exclude the other. So guys, the first one is wavelength. Wavelength is actually represented by the Greek letter lambda, which looks like the thing that I drew in red on the right side of the screen. So guys, this is the Greek letter lambda. This is technically what it looks like as a Greek letter. But if you can draw something like this, that's lambda. It's like a backwards H without much of a hump on it. Or an upside down ski wampus Y. But guys, this is the Greek letter lowercase lambda. And lambda is the distance, wavelength is the distance between two repeated points on a wave. Again, it could be peak to peak, trough to trough, inflection to inflection point. Doesn't matter. It's the distance between two repeated points. Now guys, the question is this: what will the units be for wavelength? What are the units? Meters. Yeah, so they're in units of length. How long is the wave? And so for us, it'll be meters. Although you will see that frequently we'll use nanometers, because nanometers, 10 to the negative ninth, is on the order of where visible light sits. And we'll talk more about that in a minute. So guys, the other one that we need to talk about is frequency. Frequency is represented by the lowercase Greek letter nu. So we'll talk about lambda and we'll talk about nu. Lambda is wavelength, frequency is nu, but guys, you got to be careful. This character right here, obviously, what are you going to confuse it with? V, right? So guys, grab your AP equation sheet and make sure that you see the way they represent V. Oh, I'm sorry, not V, but nu. Because you'll find on the other, wait, did they pull it?
No, it's on the back.
Yeah, so you'll see that on the page 4 side under gases, liquids, and solutions, they've got kinetic energy per molecule is 1/2 mv squared, where v is velocity. You see it capitalized?
When you were talking about density?
No, that's volume. So this is the one we're talking about there. Yeah. Understand they do look the same, but they're on different sides of the paper. So here it's nu, and here it's v. So because the constants run with the equations, I think you'll be okay. Okay, so guys, you already know this, but let's talk. What is frequency? Frequency is the number of crests, the number of repeated points, however you want to think about it, that pass a fixed point in 1 second. Now, what are the units for frequency? They're both, actually. That's great that you knew they were hertz, probably from the reading. So guys, they are hertz, but hertz are inverse seconds, or cycles per second. So the number of occurrences per second. So guys, with that said, because Matt brought it up, we can talk about it only briefly. Don't get too involved in this. But guys, there is another descriptor of waves, and that is what is called amplitude. How tall the waves are. Understand that as we talk about electromagnetic radiation, it is not important for us to understand amplitude. Other than, we've got to make sure you're not confused, because many times people will think that amplitude is a measure of brightness. Can you see how if frequency and wavelength tell us color, then wouldn't the amplitude of the wave tell us brightness? I mean, I think it's a logical conclusion maybe that if frequency and magnitude are color, then maybe brighter light is taller light. And guys, that's not at all true. We'll talk about brightness even in a minute. But guys, understand brightness is not a function of amplitude. Brightness, again, is actually a physical, it's a human experience. And it's based upon, well, I'll just tell you, it's not based upon amplitude, it's based upon the number of waves that contact your eyes. It's not the amplitude, it's you'll see. But understand that's not the case, yeah.
Yeah, it's like how many wavelengths gets your car's radio thing. That's why it makes it clear.
Yeah, yes, that's true. Yeah, you got it. Okay. So guys, you good on frequency, you good on wavelength? Okay, so now what we're going to do is we're going to bring these things together. So here's the transitional thought. Say that this is electromagnetic radiation. How fast is it going? Speed of light, right? If you could, and so maybe we should say this, guys, where is frequency represented in this picture? It's not. You can only represent frequency in a video. right? This has got to be moving for us to know frequency. I mean, thinking about like if you were to take a picture of the ocean, could you determine the wavelength? Yeah, measure the distance between the waves. But could you determine the frequency? No, it needs to be in motion. Well, guys, the same thing is true here. Frequency cannot be represented in this video because it's got to be moving for you to know how many are moving past a point. With that said, say that this were moving. If it's light, how fast is it moving? The speed of light. Here's an interesting question, or an interesting thought. The speed of light is actually a function of the frequency and wavelength of electromagnetic radiation. So write it down and then we'll derive, if you will. Although it's not, I know, you hear that from your math teachers and you're like, why don't you just give us the stinking equation? I get it, I'm like that too. Guys, we're not deriving something, we're bringing two ideas together into an equation. So if you don't understand what this sentence is saying, consider this. Speed is equal to lambda nu. Write it down. Is this true? It is. But guys, why is it true? Well, do this. Put units on these numbers. Go to the right, and before I show you, just do it. Rewrite the word speed, and then put equals, and then put the units for lambda and nu that you just learned. So what is lambda? It's wavelength. What are the units? Meters. What is nu? It's frequency. What are the units? Inverse seconds. So guys, it's this. And when you multiply meters by inverse seconds, you get meters per second, which is speed. Do you see how that fits together? But guys, now we got to bring this full circle. What are we talking about? The speed of light, which is actually abbreviated c. Einstein's equation, E equals mc squared. C is the speed of light. C is actually the constant that we use to represent the speed of light. But guys, here's the trick. You ready for the deep thought? This is a constant. So if this is a constant, what happens if the wavelength of light goes up? Its frequency goes down, and vice versa. But guys, that is exactly what we established right here. In this slide, we established that if we've got high frequency light, so this is high frequency, what's true of its wavelength? Is it high or low? It's short. So high frequency light has a short wavelength. What about low frequency light? Long wavelength. So guys, these are inversely related, and the relationship that tells us so is C is equal to lambda nu. So as the wavelength gets longer, the frequency gets smaller. As the frequency gets higher, the wavelength gets shorter. They're inversely related because C, the speed of light, is a constant. No, it's everywhere. Be careful. It's everywhere. Yeah, they are always inversely related. Yeah. Yep. All right. So here we go. So we're good with this idea? Then let's calculate this. Here's what it says. It says the yellow light that's given off by a sodium vapor lamp used for public lighting. Have you ever seen these things? Like if you go to a outdoor like park, you see them. Yeah. If you've ever been like to a park, even here in Orem, and they've got the lights that automatically kick on. They're big. A lot of times they buzz. And the light that comes off of them is sort of yellow tinted. Guys, the reason that that's the case is that the light bulb that's inside of there is actually full of sodium vapor. And a current passes through it, and it excites the sodium atoms, and they re-radiate light. Well, guys, the light that is coming off of those sodium vapor lamps has a wavelength of 589 nanometers. The question is, what's the frequency? You've got 30 seconds to solve it. If you guys are typical, more than half of you are going to get it wrong. which I probably shouldn't have said because now many of you will pick your mistake, but. So guys, I'm going to solve this on another sheet of paper, on a clean screen. So, C is equal to lambda nu. C is 2.998 times 10 to the 8th meters per second. We were given the wavelength, and we want to know the frequency. So what was the wavelength? 589? So 589 nanometers. What's the yeah but? It's got to be in meters. So guys, you could spend the time to do the dimensional analysis and convert. I strongly discourage that. Don't try to put this in proper scientific notation. Here's all that you need to do. If you're given a length in nanometers and you need it in meters, just do this. Just add times 10 to the negative 9th. In proper scientific notation, it should be 5.89 times 10 to the negative 11th. Don't do that. It's another mathematical step that's going to screw you up. So guys, just add the times 10 to the negative 9th and you'll be good. Oh, thank you. Yes, thank you. No. Yeah, thank you. No, I'm sorry. That's now in meters. Yeah. Okay, so now let's do the math. So we've got 2.998 times 10 to the, 2.998 times 10 to, thank you. Okay, times 10 to the 8th, and then divided by 5.89 times 10 to the negative 9th. 580, did I say point? Sorry, 589. So our frequency then X is 5.09 times 10 to the 14th. Now guys, what are the units? Could be hertz, Hz, or I prefer that. I prefer inverse seconds. I've never seen, I wouldn't. I've never seen that. So are you saying could you do like this? I wouldn't. I would either put hertz or inverse seconds. I've never seen that convention. So guys, what does this then mean? Well, tuck this away in your brain for a second, and let's go back here. So, what was our wavelength? How many nanometers? 589. Here's 500, here's 600. There's about 589. What color is it? Yellow, right? But then when we come up here to wavelength or to frequency, that places us somewhere in here. So here's 10 to the, frequency. Here's 10 to the 14th. Here's 10 to the 15th. We're like smack between 10 to the 14th and 10 to the 15th, which would be supported by the data that our frequency was at 1.4 or something like that. Times 10. So we're right in the middle in terms of frequency, so our numbers are lining up. Does that make sense? Okay. So guys, we understand now that there's a relationship between frequency and wavelength, and given one, we can solve for the other. You okay? Okay. So now guys, to wrap this up, we're going to relate this to energy. So how does this relationship come together? Well guys, now we're going to start talking about what this has to do with atoms. See, we can take any kind of energy, any kind of light, any kind of electromagnetic radiation, and if we know the frequency, we can figure out the wavelength. So now it's time to tie this back to atomic structure. And guys, as they started understanding that light was being released by falling electrons, they discovered that when these electrons and atoms fell, that they weren't seeing all the colors of the rainbow. They were seeing some colors that were there and some colors that were not there. Starts to sound familiar, right? Okay, so guys, the person that first really dug into this was a guy named Max Planck, or Planck, maybe more correct. And here's what he learned. He learned that when atoms release energy in the form of light, guys, this light comes in discrete chunks of some minimum amount, some minimum size, if you will. And he gave these chunks a name. He termed them quanta. So, guys, these things that we call quanta, well, it turns out that for any particular color of light, these quanta had a fixed amount of energy. So all yellow light had the same amount of energy within, not just yellow, because yellow is many different. There's deep yellow, bright yellow. But if we had one particular color, that color of light had a quanta associated with it with a fixed amount of energy. And he actually then started to term these things photons. And guys, you can think of photons as being packets of light energy. So what does the amount of energy in a photon of light, in a quanta of light, depend upon? Well, the answer is its frequency. The amount of energy in a single photon of light is dependent upon its energy. I'm sorry, frequency. So energy is dependent upon frequency. And so Planck took this idea and actually turned it into an equation. This is also on your AP cheat sheet, so I don't know that you need to write it down. But it says this. It says that energy is equal to h nu, not hv. That's nu, that's frequency. And guys, h, E is obviously energy. H is what is called Planck's constant. And its value, which is on the AP sheet, is 6.63 times 10 to the negative 34th joule seconds. And then, guys, of course, V is frequency. So what Planck figured out is that when elements emit energy in any particular color, the amount of energy that comes off is a multiple of HV, H nu. So let's do this. And guys, if you need to come back and write this down, you can. But again, it's in your AP cheat sheet, so you need to be smarter about how you take notes. So guys, let's do this. Let's figure out the amount of energy that this yellow light is giving off. So here we go. We're going to figure out the amount of energy that this yellow light is giving off. But look, hey, there's our yellow light. We already know the frequency. We were given the wavelength. We figured out the frequency of the light. What can we do to now turn this into an amount of energy? It's our next equation. E is equal to h nu, where h is 6.63 times 10 to the negative 34th joule seconds, and that's multiplied by 5.09 times 10 to the negative 14th inverse seconds. When we do that, seconds cancel and we're left with joules. Did anyone get the answer?
Yep.
What is it?
3.37 times
10 to the negative 19th joules. So guys, what does that mean? Well, here's what that means. It means every photon of light that comes out of that yellow vapor light that's lighting up your basketball court, every photon of energy that comes out of there has this amount of energy associated with it. This many joules of energy. So if one photon hits you, boom, that much energy. Two, twice that. Three times that. But guys, that light can only emit energy in multiples of this number because this is the amount of energy that each photon that it releases possesses. Do you get the idea? So then what happened was Bohr came back and built upon this idea of this energy being contained in light. And guys, this is our transitioning thought. What Bohr figured out is that amount of energy is actually representative of how far the electron fell. Does that make sense? So those 3 point whatever joules of energy is actually a representation of how far the electron fell. And what he figured out is if we know where that electron fell to, and then if we can figure out how far away from that this many joules of energy is, we can figure out how far it rose, and we can figure out the electron structures. And that's where we're going to transition next time. So guys, let me give you your homework, and we will call it a day. There it is. So guys, when I see you on Friday, we will grade this homework, and we will then talk about relating energy to electron structures. It's fascinating. Or Wednesday. You can tell I'm scattered today. No, you're good. So guys, this is where we're going to pick up next time.